Good afternoon.
Hello, everyone. Nice to see you guys.
Hello.
Hi.
Good afternoon.
Good afternoon. How are you doing? Yes, preparing for the midterm.
Yeah.
Good. That is important.
And can I ask a question regarding the midterm exam?
Sure.
Yeah, will be there any mock exams or practice sheets to practice?
I mean, you practice every week with homework. That is.
Yeah. Maybe for someone of us, that's not enough for.
Oh. Yeah, but then no one stops you to solve additional problems from the textbook.
From textbook.
Yeah.
Okay.
That will be more or less plus minus in terms of complexity, something in the range what textbooks provide. Of course, not from the textbook which you are working on. There will be other problems, but they will not be much fundamentally different from those.
Okay.
Mm-hmm.
Thank you.
You're welcome. Yeah, practicing in solving problems is very important because someone had more practice during school, someone didn't solve so many problems, and obviously it could be a bit more challenging to deal with this, and probably would be nice to the more problems you solve, the bigger chance that you will see something similar on the midterm and the final exam. Of course, their problems are different, but the concepts behind them quite often are very similar. And if you already solve a bit similar problem, that will be very helpful to you during the exam. Okay, so we during our sorry about that. During our previous discussion, started this new topic, considered the features of this equation which describe gravitational force, that it's proportional to masses of two objects which interact and reversely proportional to the square of the distance between them. Also introduced three Kepler's laws, which were obtained based on very long-term empirical observations and analysis. As I mentioned previously, today I would like to come back again to this equation of gravitational force and show you how the combination of the way how you can combine laws of motion and Kepler's laws, which all of them are empirical laws. They were not derived from some theories and models. They were just obtained based on observations. How you can combine them in order to approach the derivation of this equation for gravitational force with accuracy to some constant. And this constant was actually a bit later after the publication of like Newton's publication of this gravitational force equation was determined experimentally by Henry Cavendish, British physicist. By the way, the physics department of Cambridge University actually is called Cavendish Lab, and there is a honor position, Cavendish Professor at Cavendish Lab, which was occupied by a bunch of Nobel laureates in the field of solid state physics and semiconductor physics. But initially also, that was one of the most famous Cavendish professors was Rutherford, who discovered the structure of the atom. So quite connected trace of trend of development of science and with the roots and even current conditions. Now, as I know, the Cavendish professor is Henry Snaith, Richard Henry Snaith. He works in organic and perovskite photovoltaics, which is quite close to my field of, which is actually my field of research. That's why we are kind of familiar with this, his lab and his research. So coming back to the gravitational force, now let's try to derive this equation based on laws of motion and Kepler's laws. So let me change the screen. And first of all, first comment which we should take into account is that the first Kepler's law claims that planets are moving along some elliptic orbits. However, these elliptic orbits in our solar system are quite close to circular for most of the planets. So this eccentricity of elliptic orbit is quite small and close to zero. It's not circle, like ideal circular trajectory, but very close to circle. So that's why considering circular trajectory is really justified, and moreover, it gives us opportunity to avoid unnecessary complex calculations. So we stick to circular trajectory, and as next step, second law of Kepler's law claims that the movement of planets about the sun by circular orbit is happening with constant linear velocity. So we remember from second Kepler's law that in general it states that the radius vector sweeps the same areas, like equal areas, over equal interval of time. And if we consider circular orbit, that means that linear velocity should be constant. Now, according to the third Kepler's law, we remember that it was formulated as period square is proportional to the cube of the radius. So in other words, we can write that the ratio t squared divided by r cubed is constant. So taking this into account, and now we can proceed further with circular motion. With circular motion, like with constant velocity, linear velocity, we have only centripetal acceleration, which is v squared divided by r. And r is the radius of this orbit. In its turn, velocity, linear velocity, can be represented in terms of radius and period. That will be 2 pi times radius divided by this period t. So if we have this, we can substitute expression for linear velocity in terms of radius and period in first equation and get expression for centripetal acceleration in terms of radius and period. So that will be 4 pi square times r divided by t squared. So now we have this. So we, as you understand, we want to have this in terms of radius and period because we want eventually have a link to this third Kepler's law. So this we have. Now we need to address to second law of motion. We know that in general, acceleration is equal to force divided by mass. So this we remember. Keep in mind that at this point, we don't define anything about specific mass, just some force. That also will be true for centripetal acceleration, right? A centripetal is equal to, so here we deal with just magnitudes of these vectors. So there will be centrifugal force, let's mark it as Fs. And that is divided by some mass. That should be equal in terms of radius and period as defined by this expression. So it will be 4 pi squared times r divided by t squared. Okay, so now we need to consider the fact that our system is in equilibrium. So we have some steady state. The radius doesn't change. That means that this planet is continuously orbiting the sun along this circular trajectory. In that case, if we consider just in absolute values, the magnitudes, the centrifugal or centripetal force is just a matter of frame of reference, actually the same physical meaning. So it's equal to the gravity force. So we need to compensate centrifugal force in order to keep the planet on this orbit, and that is the job of the gravity force, which is defined by interaction via the gravitational interaction between the sun and the planet. So in this case means that we can just substitute this Fs with Fg because they are in magnitudes are equal. So we can write that F gravitational divided by mass is equal to 4 pi squared times radius divided by t squared. So now, in order to make it closer to the definition of third Kepler's law, let us multiply left and right side of this equation by r squared. So we will get the following. So here will be F gravitational times r squared divided by mass m, and that will be equal to 4 pi squared times r cubed divided by t squared. So as you see, in the right side of this equation, we have a constant, because 4 pi is constant, r cubed divided by t square, according to the Kepler's third law, it is also a constant. So here we can write that this is some constant. Now we can express gravitational force. F gravitation is equal to some constant times mass divided by r squared. So this is very rough in terms of just, so it tells us that it's proportional to the mass and reversely proportional to the square of the distance with some constant. However, we also understand that it takes two objects with different masses, or the same but two masses, for gravitational interaction, because you need to have two objects which possess some mass in order to interact with this gravitational force. And in this particular case, it's the sun and the planet. So here we should also should take into account the mass of both. So that's why we can write that it will be some constant times mass of the sun times mass of the planet divided by r squared. So this is actually almost the same what we wrote at the beginning for gravitational force. It's actually the same, but this constant is not defined here. So we know that it's gravitational constant times mass of the sun times mass of the planet divided by r squared, which is the distance between them. This constant initially it was not defined, so it was just a constant, but the numerical value was calculated, as I mentioned earlier, by Henry Cavendish in 1798. It was after the original publication of Newton's work. However, based on purely empirical observations, which resulted in laws of motion and Kepler's laws, we are able to derive within some constant the equation which describes gravitational interaction, which is quite nice. So now let us proceed further in our discussion and address such concept as gravitational field. So the thing is that it's not so obvious how objects can interact with each other without being in direct contact. So we know from previous topics which we discussed, for instance, friction force, you need to have a contact between the surface and the body. Also, when bodies hit each other, there is some deformation of these bodies. That deformation results in some spring forces which are exerted on other bodies, and that causes objects to fly away from each other after collision, for instance, if it's not inelastic collision. So any type of force which was considered previously exerted on a body was associated with some external body being in contact with the considered body. And now we are talking about gravitational force, which doesn't require this intimate contact of bodies, can act on any distances, and can have a just quite significant influence on the environment and nature in general. So the nature of this interaction was not clear for Newton at that time when he published his famous works. And this explanation came later when there was a introduced concept of fields, and in particular gravitational field. The numerical a quantitative description of this field is described by strengths of the field. And in order to approach this concept of the strengths of the gravitational field, we can consider the following situation. Let's say somewhere next to the surface of the Earth, or just in some location next to the Earth, we place some object with a mass m. So then we know that there will be some force acting on this object, which was gravitational force, and the strength of the gravitational field is given as, it's a vector quantity, it's given as a gravitational force divided by mass m. So if this experiment is carried out, for instance, on the surface of the Earth, or close to the surface of the Earth, we consider this g as the acceleration of free fall, and that is the strength of the gravitational field in this given condition. However, in general, it will be a function of distance from the planet, also a function of the mass of the planet next to which we consider this. So if we consider this next to the planet Earth, then in general case, we can write that strength of gravitational field is equal to this gravitational force divided by m, and that will be equal to minus g times m Earth divided by r squared. And here we can put this unit vector for position vector, which defines the direction. So we have this minus here, means that gravitational field is pointed towards the center of the Earth. So this is a quantitative parameter which describes gravitational field. And if there is some gravitational field and it exerts some force on bodies placed in this field, obviously there is some potential energy of this field. And that's what we need to discuss and quantify now. So how do we define potential energy previously? We have kinetic energy, mv squared divided by 2, and we have potential energy. What do we write for potential energy?
mgh.
Yes, mgh. We assume that our object is somewhere close to the surface of the Earth. G is considered then as a constant, and we just need to deal with the height of the position of this object with respect to the ground level, which is the Earth's surface. However, in general case, we need to take into account that g, strength of the gravitational field, is a function of distance from the planet, from the center of the planet, and it will change. So in order to address this dependence, it's not a constant. We need to consider this potential energy of gravitational field in general case. So change of the potential energy is equal to the final potential energy minus initial potential energy. And that by definition, we discussed this earlier, is given as negative work done by conservative internal force in the system. So we have some isolated system. We have isolated system, let's say our planet Earth and some object with mass m, isolated from external environment. There's no other forces acting on them. And in that case, we write that it's equal to negative work done by moving this object in from initial to final position. And here is some conservative force, which is a function of position times dr. So this conservative force in this isolated system is actually our gravitational force. And we can write that F as a function of R is equal to minus G times mass of the planet, mass of the Earth, times mass of the object divided by R squared. So this minus here means that we have this attractive force. So it attracts body towards the center of the planet Earth. And now we can substitute it here in this integral and get expression for the change of the potential energy. So that will be U final minus U initial is equal. So we can already, we have minus and minus here. It will give us plus. And we can take out from integral the constants, which will be G mass of the Earth, mass of the object, and will be integral RI, RF, like initial and final position of the body, dr over over R squared. So when we integrate this, we will get, here are our constants. Then integral will be minus 1 over R from Ri to R final. And that will be, we can take this minus in front. Will be minus gravitational constant mass of the Earth times mass of the object, 1 over R final minus 1 over R initial. So now we can define the zero potential energy arbitrary in any point we want, but physically makes sense that, for instance, if we consider that initial point from where this object started to move was infinitely far from the planet Earth. So if we consider initial position as infinity, then initial potential energy should also, let's say it approaches infinity, that also will approach zero. So we can consider that at Ri infinity, then it's in the denominator. So this term with minus will be 0. And this initial energy will be also 0. So then we can actually go from the difference of potential energy to the absolute value of potential energy, because initial potential energy is 0. So the any change of potential energy will give us the absolute value of potential energy. So in that case, we can write that potential energy as a function of position with respect of the center of the Earth. Will be given as gravitational constant times mass of the Earth times mass of the object. Here will be minus, and that divided by r. So it's actually how we get it. It's this minus is here. This is our numerator, and instead of final, we just use r, which defines position with respect to the Earth center. So now we have potential energy of gravitational field, and that is specifically written for the system Earth, some object, but that is also valid for any system, any combination of objects. That's why in general we can write that potential energy is equal to minus g times m1 times m2, which two objects are in interaction, divided by r, which is distance between these two objects. This minus stands here and shows that so this potential energy is negative because the force is attractive, and it's necessary to do some work in order to separate objects which interact via gravitational field with each other. So this means that our next question which should be discussed is actually energy consideration of gravitational field. And that is good to consider on example of some planetary or satellite motion also. So let us assume that we have our sun and some planet which is moving about the sun along some circular trajectory orbit. So here will be some linear velocity vector of this planet, and this is the radius position vector with respect to the center of the sun. So we assume that mass of the sun is much larger than mass of the planet. That's actually true. So that's why, because indeed this system is rotating about some center of mass of these two objects. But having this statement that mass of one object is much larger than the mass of the other, then we can, with respect to some inertial system of reference, we can assume that the velocity of the sun is equal to 0. So it's kind of stationary, and planet is moving about it with some linear velocity v. So total energy of such system will be the sum of kinetic and potential energies. We already know expressions for both, so we can write that total mechanical energy is equal. Kinetic, it's 1/2 m of the planet times linear velocity vector, linear velocity square, minus potential energy. We have this equation here, which is minus G gravitational constant times mass of the sun times mass of the planet divided by R, which is the distance between the sun and the planet. So let us now come back to the second law of motion. So we know from second law of motion that force is equal to mass times acceleration. And here we deal with gravitational force and centripetal acceleration. So from here we can write that gravitational force G mass of the sun times mass of the planet divided by R square is equal to mass of the planet times centripetal acceleration, which we can express in terms of the linear velocity, v squared divided by R. So now, in order to make it convenient for further consideration, let us multiply the left and the right side of this equation by 1/2 of the radius divided by 2. So let's see what we get. If we consider this right side first of the equation, that will be 1/2 mass of the planet times v squared, so which is actually kinetic energy of this motion of the planet, will be equal to G times mass of the sun times mass of the planet divided by 2R. So we see that we can express kinetic energy of the moving planet in terms of the mass of the sun, mass of the planet, and distance between these two. So that's already quite interesting relationship. And we can proceed further. Now we can substitute kinetic energy by expression in terms of masses of the objects and distance between them, and rewrite the expression for the total mechanical energy. Let's go to another slide. So E is equal, let's check here. So what we have, GMS MP divided by 2R. GMS times MP divided by 2R. And here we still have potential energy. So that was G times MS times MP divided by R. So eventually we get the total mechanical energy is equal to GMS times MP divided by 2R. And here we have minus. So that is another important equation because it tells us total mechanical energy already in terms of masses of the sun and planet and distance between them. And what is also important, since this is isolated system and there are no other forces acting on this system from outside, that this total mechanical energy follows the conservation of energy, so it stays constant and doesn't change. So now we can write that if, for instance, we know initial parameters which define initial total mechanical energy, then we can use this value because it remains constant for final state and determine some unknown parameters from this. So let's say if we have 1/2 times mv initial square minus, so this is initial kinetic energy, times g ms mp divided by r initial. Then if we change, for instance, the radius of this orbit, then it will cause the change in velocity. And we can determine it because we know that the final condition, mv final square minus g ms mp r final will result in the same total mechanical energy as initial condition. So that can be used for practical applications and in solving some problems related to the motion of planets and satellites. So now I think we don't have enough time to start the consideration of escape speed, which comes as a consequence of this conservation of mechanical energy potential and kinetic energy of planetary or satellite motion. So we will do this in detail during our next discussion on Friday, in order not to be in a hurry and discuss some moments which can be interesting about this escape speed. And at this point, I believe we can finish or address your questions, if any, according to the gravitational interaction in general. Any questions now? So during this discussion, we have shown with which thinking you need to approach, show the way of thinking in the approach for derivation of equation which describes gravitational force based on known empirical laws of motion and Kepler's laws, which I think quite interesting. It's not in the textbook. However, I believe that's quite interesting link between this previously studied laws of motion and Kepler's laws and the equation for gravitational force. And also we introduce a new concept which explains the mechanism of this gravitational interaction via a gravitational field that allows two bodies interact with each other without being in direct contact, which is very important and different from other types of interactions we considered so far. So we derive the equation for strength of gravitational field as a function of distance. And based on that, since there is some force exerted on mass placed in gravitational field, we also calculated potential energy of this gravitational field in general case, which is not just mgh with respect to ground level of the surface of the Earth, assuming that strength of the gravitational field is constant. But in general case, when strength of gravitational field is changing as the distance from the source of this gravitational field increases. Then the source of gravitational field in our discussion was planet Earth. It could be any other planet or heavy object. or like any object, but we deal with heavy objects because those create enough strong gravitational fields which we can experience. And also we discussed the conservation of total mechanical energy in a system, planet, satellite, or sun, planet, where we have shown that it's possible to express kinetic energy of the planet moving about the sun in terms of the mass of the sun, mass of the planet, and radius, which is interesting. And then also that it's possible to get the expression for total mechanical energy in terms of the same parameters as mass of the sun, mass of the planet, and distance between them. This energy is conserved because it's considered as an isolated system, and that's why we can apply conservation of energy for such a system of which describe the satellite or planetary motion, and of course use this for solving some applied problems in these cases. Okay, thank you very much for attention. Have a good day, take care, and see you on Friday. That will be our last lecture discussion before the midterm, and actually before the fall holidays.
Thank you
Thank
very
you.
much.
Bye. See you later.
Thank you. Goodbye.
See you guys. Bye bye. Take care.
Thank you. Goodbye.
Thank you.